Hello everyone, my name is Yuan Ren. I'm a PhD student from Inclusive Interaction Lab at the University of California, Merced, advised by Dr. Ahmed Arif. Today, I will present my work, investigating a force-based selection method for smartwatches in a one-dimensional phase loss study and two new character-level keyboards. Smartwatches are becoming increasingly popular among mobile users. Today, 1 in 5 US adults regularly wear a smartwatch or fitness tracker. Global demand for smartwatches also increased by about 40% in 2021 compared to the previous year. Yet, selecting small targets is difficult and error-prone on smartwatches due to the fat finger problem. To address this, most smartwatches either clutter the interface by using many large interactive elements or requiring performing a sequence of actions. Both of these approaches affect performance and user preference. We propose a new target selection that enables adjusting the cursor along the x-axis by variating contact force on the screen. We focused only on the x-axis as we envision force as a companion of touch rather than an independent selection method. First, we conducted a user study to identify the levels of force users can comfortably apply to a smartwatch to map the most comfortable range of force to cursor movement. We used an iPhone X to simulate an Apple Watch 5. The surrounding area of the simulated watch was touch insensitive to avoid the effects of accidental touches. We use a smartphone instead of an actual smartwatch because current smartwatches do not provide the support for continuous force detection. We also used a silicone wristband to attach the phone to the user's wrist like a smartwatch to increase the external validity of the study. In the study, participants applied soft, regular, and hard forces on the display. For regular force, they were instructed to apply the force they would usually apply on a touchscreen, while the soft force is softer and hard force is harder than that. No further instructions were provided. The app displayed one force level on the screen. Participants touched the screen and changed contact force as instructed, without compromising physical comfort. We normalized the available force value from 0 to 6.67 to 0 to 1 for better presentation. The median force applied for soft, regular, and hard tasks were 0.1, 0.39, and 0.55 respectively. We used half the standard deviation from the median of the soft force at the lowest value and about twice the standard deviation from the median of the hard force at the highest value, which give us the range from 0.05 to 0.8. We used different strategies here to select the lowest and the highest force values because while participants were fairly consistent in the minimum force levels, the maximum force levels varied widely. In about 10% of all incidents, participants applied a maximum force level closer to 0.8. From the figure, you can also see that the force value rarely went outside this range. This suggests that they are comfortable with this force level. Participants also confirmed this in the post-study interview. We then mapped the force range to cursor movements along the 368-pixel horizontal space of a smartwatch using a linear function. Second, we conducted a one-dimensional phase loss study to compare target selection performance of tap and force tap. One-dimensional phase law experiments combine serial responses with one-dimensional movements. The targets of width W are placed on the two sides of the display. The target to be selected is highlighted. Upon selection, the opposite target is highlighted. This back and forth selection continues until all targets are selected. Each movement covers an amplitude A, which a distance to the center of the target. The dependent variables in the phase loss study are the movement time and throughput in bits per second. We used 10 pixel, 40 pixel, and 80 pixels for widths based on recommended widths in the literature. We used 80 pixels, 140 pixels, and 200 pixels for amplitude to assure that targets do not overlap or go outside the boundary. This is an overview of all tasks in the study. In total, 9 sequences were generated based on the 3 different amplitude and widths. In the study, participants complete 20 trials per sequence. Overall, tap yield significantly higher throughput than force tap. The interaction effects suggest that throughput of the 2 methods were significantly affected by the target size and amplitude. Force tap performed significantly better with the smallest targets, while the tap performed significantly better with the bigger ones. For movement time, overall, force tap was significantly faster than tap. Selection time for the smallest targets was significantly slower with tap than with force tap. Selection time for the larger targets was somewhat comparable. In the figure, you can see here is a clear split between the targets of width 10 pixels and the targets of width over 10 pixels. A significant effect was identified on frustration. Participants were significantly more frustrated with tap than with force tap, primarily with the smaller targets. However, they found both methods relatively similar in terms of mental, physical, and temporal demands, performance, and effort. Based on the findings, we recommend enabling both tap and force tap on smartwatches. Tap is fast and reliable for bigger targets, but for those occasional smaller targets, force tap is much more reliable, faster, and causes less frustration. To demonstrate practical usage of force input, we designed 2 slide and force keyboards. One is slide force keyboard, and the other is slide force slide keyboard. Both uses alphabetical layouts and enable users to enter 1 character at a time using force tap and finger slide gestures. We used text entry as a test scenario because entering text is an extreme case of target selection, requiring repetitive selection of different targets. In this case are the keys. The keys are of width 7 pixels, which is much smaller than the smallest target used in the previous study. Note that, unlike the previous study, here we combine tap and force tap. The position of the finger is used to place the cursor closer to the target. Then the cursor position is adjusted by varying the contact force for precise selection. To enter a letter with the slide force keyboard, the user slides the finger horizontally along the x-axis anywhere on the screen. The 5 letters closer to the x-coordinate of the fingers are magnified using a zoom-in effect. The user then fluctuates the force to navigate between these letters. Lifting the finger confirms the selection. For slide force slide keyboards, it requires the user to apply extra force to replace the keyboard with magnified versions of 5 letters. The user slides the fingers to navigate between the letters. Lifting the finger confirms the selection. We conducted a user study to compare the keyboards. We didn't find a significant difference between slide force and slide force slide keyboards in terms of entry speed and accuracy. The words per minute were 4.3 and 4.2 for 2 methods respectively. A significant effect of block was identified. Words per minute for both methods improved about 20% in the last block compared to the first. In summary, we investigated the possibility of using contact force as an active mode of interaction on smartwatches, especially for the selection of smaller targets. We presented the results of 3 user studies. The first, identify the most comfortable range of force users can apply on smartwatches. The second, reviewed that the force input is significantly more effective in selecting smaller targets than touch. The final study developed and compared two new force-based character-level text entry techniques to demonstrate that force could be effectively used in practical scenarios. Besides, the novel character-level keyboards proposed in this work can be used together with predictive keyboards to enable the entry of out-of-vocabulary words. And that concludes my presentation. Thank you very much, and I'm ready to take any questions.